one of the first days we started talking about methane as a fuel, and we looked at what the overall reaction would be. And we identified this as an 8-electron process. So we took methane and we burned this with oxygen ions in an SOFC. We are going to make a CO2 and 2 waters. And to do that, we're going to have to pass 8 electrons because each oxygen ion is charged 2. So this is what's happening at the anode, and then at the cathode, we're taking 2 oxygen plus 8 electrons going to 4 O2 minus. And so if we talk about the extent of reaction, like how if I have a mole, 1 mole per second of this reaction going on, it would mean we're consuming 1 mole of methane. So we could talk about xi dot on a methane basis. The way we've been thinking about this with hydrogen, you might think you could do something like this. So I'm defining extent as the consumption of the methane. And then I'm defining a fuel utilization. So I'm saying that 1 minus the utilization times the amount of methane going in, that would be the remaining methane that we're leaving unconsumed, right? So this would work. The problem is the reactions I've just written are not really what's happening. We put in this methane, and what happens to it? Well, it undergoes steam methane reforming. So we're consuming some of the methane and forming hydrogen, some CO, maybe the water gas shifted reaction is happening. So you got all these other molecules going in and out, and they're also reacting electrochemically. And in fact, most people think that methane doesn't react directly anyway. It always has to go through some type of intermediate like CO and hydrogen. So this kind of just doesn't work. We can't really define either xi or utilization on this type of basis because methane is not the only fuel molecule. So I have to think a little bit deeper, like what's actually happening and how does that affect a couple of things? One, how does it affect Faraday's law? How does it affect our material balance considerations? How do we define the extent of reaction in a system that has multiple reactions happening? Or how do we think about the utilization of the fuel? Let's think about steam methane reforming for a second. We're taking methane and we're reacting with water to form hydrogen. And we're also making a carbon monoxide. So this is SMR. And let's say there was no water gas shift. Right, we just make hydrogen and CO in a 3-to-1 ratio. And then the hydrogen and the CO get consumed as fuel molecules. So 3 hydrogens. For each H2, we would need 1 oxygen. So that would be 3 O2 minus. And that's going to take us to 3 waters and liberate 6 electrons. And then we have 1 CO molecule. And if we oxidize that to carbon dioxide, that is 2 more electrons. So we add all that up, and it's 8 electrons. So that's interesting, because so what's saying is, even though I'm taking the methane, I don't react it directly, I'm converting it to other molecules. When I count all the electrons needed to fully oxidize those ring molecules that we do make, it's still 8 per methane. So now consider steam methane reforming and water gas shift. So we're going to take CH4 and H2O, and we're going to make 3 hydrogen and CO. But then I'm going to take the CO and I'm going to react with water again to make CO2 and another hydrogen. So these two cancel. We're consuming and producing CO. And so the net effect is we're making CO2 and 4 hydrogen. So now we take those 4 hydrogen. That's going to react with 4 oxygen ions and take us to a 4H2O plus 8 electrons. So again, even with water gas shift, it's still 8 electrons. And I think that makes sense because all of these steps, these are chemical reactions, right? So this is all chemistry, not electrochemistry. We're not transferring ions or electrons across the cell for any of those reactions to happen. They're all happening just in a catalyst bed or in the pores of this electrode material in the gas phase or on solid surfaces. Those are chemical reactions. They're happening. They don't involve ions or electrons. They're redistributing the atoms on different molecules. But at the end of the day, we're doing the same thing. We're taking all whatever hydrogen, methane, CO, and we're oxidizing them to water and CO2. So when that's all done, we're passing the same amount of current. So in a sense, Faraday's law is preserved, even though we're converting to other molecules and fuels. This leads to the idea of something that's sometimes called a hydrogen equivalent extent or utilization, which tries to leverage this idea. The easiest way to think about it is actually in terms of atomic balances. So if we think about our anode compartment, we've got our cell, we're feeding in fuel, and within this fuel stream, I can track carbon atoms, hydrogen atoms, and oxygen atoms. Through the cell, I'm passing oxygen ions. So O2 minus is coming through the cell, and it's oxidizing our fuel. But no matter what happens, that's the only atomic species that we're actually passing across the cell is oxygen. We're not changing the amount of carbon. We're not changing the amount of hydrogen. So the carbon is just flowing through here, whereas oxygen is increasing. So if we think about what this fuel is composed of originally, you're coming in with CH4. We also have a certain amount of water, which is coming in because we have a certain steam to carbon ratio. We're letting those things come to equilibrium in the pre-reformer, breaking this up into CO, hydrogen, water, CO2, and remaining methane. So if we think about like a control volume around the cell or some element of the cell, we have a flow rate of oxygen atoms in the gas phase that is going to be given by, on the inlet side, by the flow rate of water that's in. And then if I look at what comes out, this is going to be whatever went in plus an extent of reaction. And if we're talking about methane, then it would be 4 times the extent of reaction. And I'm going to put a subscript on this xi just to make it clear I'm talking about a particular xi. This is the 8 electron xi. It's the 8 electron extent. Another thing we could just define is, since we don't talk about molecules anyway, there's not much point in the 8 and having this 4 running around. Then we might as well just skip to the chase and instead talk about 2 electron extent. And I think generally that's how people tend to write it. They'll talk about it as a 2 electron extent. Even though methane is consuming a lot of electrons, we can think of it as in a 2 electron equivalent. Each methane produces ultimately up to 4 hydrogen molecules. Each hydrogen molecule is a 2 electron reaction. We can talk about extent in terms of pairs of electrons, which also translates to numbers of oxygen ions that travel across the cell. And so that allows us to preserve Faraday's law. Basically, we can always still say that current is equal to 2F times xi dot, because this xi dot is written in terms of the 2 electron extent. So this becomes the equivalent of Faraday's law for mixed fuels. What that doesn't answer is, where is the oxygen? Is it on CO2? Is it on CO? Is it on H2O? That is not a question answered by Faraday's law. So we still have to be solving chemical equilibria. The good news is the chemical equilibrium, however that oxygen wants it to distribute itself on these molecules, it doesn't affect the current. It doesn't relate to the fuel utilization, because if I oxidize one species, I'm reducing another one. If I reduce one species, I'm oxidizing another one. So that ability for the fuel to do more reaction is preserved, no matter how the oxygen that you have around happens to redistribute itself. So let's say we have a mixed fuel. We've got CH4, we have hydrogen, we have CO, we have H2O, we have CO2. And we think about what is the fuel content? Like, how many electrons could we pass, or how many oxygen ions could we pass in order to fully oxidize this fuel? So for each methane molecule, if I could react methane at the anode, that would require 8 electrons or 4 oxygen ions, however you want to think about that. Hydrogen would be 2 electrons and 1 oxygen ion. CO, the same thing, 2 electrons, 1 oxygen ion. Water and CO2, they're already oxidized. They cannot consume anymore. So they have no fuel value from a Faradaic standpoint. So you could define an n dot fuel for n dot CH4 plus n dot H2 plus n dot CO. So I'm taking into consideration how many oxygen ions I would need. I'd need 4 for the methane, 1 for hydrogen, 1 for CO. And so if I wanted to account for all of the possible Faradaic reaction that this fuel could provide, it would be a sum of those 3 terms. And so we could define a xi dot as a n dot, or so n dot fuel in minus n dot fuel out. So this is the hydrogen equivalent extent, or the 2 electron extent. The way we've been doing it in the spreadsheet is, again, to look at it from an atomic basis. It simplifies our material balance problem if we think from an atomic balance standpoint. We have C, H, and O in our fuel stream. And which molecule? So C, that's on methane, it's on CO, it's on CO2. The hydrogen is part of methane also. It's part of the hydrogen, it's part of the water. And then oxygen is on H2O, CO, or CO2. Before defining an extent, imagine, let's just think about the minimum. Like, what is the absolute bare minimum amount of oxygen atoms that we could have flowing in this gas stream? And I think the answer is, what if we have no oxidation yet? The minimum oxygen possible would be if we had methane plus the water that we're feeding in as part of the steam to carbon ratio. So N dot O min is equal to the steam to carbon ratio times N dot C. That tells us how many oxygen atoms are coming in also with the water that we're using to support that hydrocarbon. And then think about maximum oxygen. Like if we completely oxidize the fuel, took all the methane, all the hydrogen, all the CO, converted it all to CO2 and water. For each CO2 molecule, we'd have 2 oxygen atoms. For each hydrogen atom that is on a water molecule, we would have half an oxygen. So between these 2 extremes, this is our fuel oxidation process. It's taking us from this amount of oxygen to this amount of oxygen. If we think about N dot H, this is also not changing with position. This is going to equal 4 times N dot C plus 2 times the steam to carbon ratio times N dot C. That counts for the hydrogen that's on the water that's coming in, and we're also counting for the 4 hydrogens that are on the methane themselves. And so if I rearrange that, the steam to carbon ratio can also be written as N dot H minus 4 N dot C, which are both constants, divided by 2 N dot C. And that's regardless of how many oxygens we pass across the cell. So I can plug this in here and solve for that. And I get that the minimum oxygen is N dot H over 2 minus 2 N dot C. And NO max is 2 N dot C plus a half N dot H. So if I think about the difference between these two, that's the maximum extent of reaction that we could get. Xi dot max would be N dot O max minus N dot O min, which is 4 N dot C. And this would be true of any hydrocarbon. So one way people will define the utilization is to say, well, whatever extent I have divided by the maximum extent That's the utilization. And so we end up with xi dot equaling 4 times the utilization times n dot c. So if we're doing an atomic balance, we're just tracking the amount of carbon that's flowing through the cell. That's constant. So there's a direct relationship, just like there is if I just have one molecule, hydrogen, I can talk about the extent as depletion of hydrogen, right? It's the same thing here. I know how much carbon is flowing across the cell. I can talk about utilization or the extent as being some utilization of that amount of carbon and taking it from a hydrocarbon state or other molecules that embody that reduced state to CO2 and water. For the moment, I want to take a step back and talk about one other thing that comes up with mixed fuels. What about equilibrium potential? Because one of the things we have to think about is we're applying a cell voltage. We need to know what the displacement is from the equilibrium potential in order to establish the driving force for ohmic resistance or overpotentials on the electrodes. If I just think about this conceptually for a second, we've talked about equilibrium of the hydrogen oxidation reaction. But now let's say we have other fuels present. And I'm just going to grab one of them because I think we can make the point with just one other fuel. So imagine we have both hydrogen and CO, syngas. We feed syngas into a fuel cell. We blow it across the anode. In principle, both the CO and the hydrogen could be reacting at the anode, and as we've just been talking about. So here's our anode, and we've got our cell. O2 minus can go across this electrolyte, and then on the other side, we're reducing oxygen. Let's imagine for a second, we pick one of them, so hydrogen, and we use the Nernst equation to calculate the equilibrium potential based on the amount of hydrogen that we have around. We would say that the equilibrium voltage would be equal to minus delta G of the reaction for our hydrogen oxidation divided by 2F. And you recall that in the past, we've taken that delta G and we've broken that up. We can talk about that as a delta G0 for the hydrogen to water reaction. Plus, we would have an RT over 2F times the log of Q, where this would have like a P H2, PO2 to the 1/2 power divided by PH2O. So delta H0, that's what we would look up in the Barron tables at whatever temperature, and then we'd add the term for the composition of the gas. But for the moment, let's just focus on this guy. And so another way to express this is just in terms of the Gibbs free energies themselves. I could write this as literally GH2 plus 1/2 GO2 minus GH2O divided by 2F. That's assuming we're in equilibrium with the hydrogen, but we've got this other molecule now, CO. It's also reacting, right? So if I forgot the hydrogen and I just said, okay, I've got CO as a fuel, what would the equilibrium potential be with CO? We would get a similar expression. But instead of CO and instead of hydrogen, we'd be talking about CO2 and water. So this would be minus delta G of CO oxidation divided by 2F, which we could write as GCO plus 1/2 GO2 minus GCO2 divided by 2F. In principle, we would get two different numbers for the equilibrium voltage. However, let's think about water gas shift. Imagine this fuel is in water gas shift equilibrium. If that's true, then CO is reacting readily with water to form CO2 and hydrogen. And if that reaction comes to equilibrium, we could say that GCO plus GH2O is equal to GCO2 plus GH2. Or another way I could write this is that GCO minus GCO2 has to equal GH2 minus GH2O if water gas shift is in equilibrium. So if I take that number and substitute it back up here in the equilibrium voltage for the CO-CO2 reaction, I just get the same equilibrium voltage I would have calculated directly from the hydrogen and water. And the same thing happens with steam methane reforming. So at the end of the day, if all of these gas molecules, if they all are coming to equilibrium with each other in the gas phase, then if we calculate the oxidation potential of the electrode based on any of them, CO, methane, or hydrogen, we get the same equilibrium voltage. There aren't three different cell potentials. There's only one equilibrium potential because of those gas phases reactions all being in equilibrium. And we can choose how we want to calculate it. You can pick any of them. Say we calculate hydrogen pressure, partial pressure, and water partial pressure, stick that into the Nernst equation, we'll calculate the equilibrium voltage. If we've done our calculations correctly, then if you take the CO and CO2 concentrations you calculated, you stick them into the appropriate Nernst equation, same number will pop back out. So we can actually use that as a consistency check in our calculations.